Hardware and software queue. In this video, I am going to talk about two types of queues that we have in one router, hardware queue and also software queue. What are the needs to the hardware queue? What are the needs to the software queue? And after that, we can talk about other features. First, as you can see here, we have a simple scenario, include PC1, router 2, and PC2. I have configured this scenario previously, and now we have connectivity between the PC1 and PC2. Let me to show you. This is the PC1. Let me to show you ping 192.168.210 result. As you can see from the PC1, now we can send traffic to the PC2 with the IP address of 192.168.210. First, let me to explain the need to the hardware queue. After that, we can talk about the software queue. About the hardware queue, it is actually a hardware queue, okay? It is actually hardware, okay, or physical queue. Other names of the hardware queue is TX queue, means transmit queue, or transmit ring, and also TX ring. All of them can be used instead of the hardware queue, but in most cases when we are talking about this queue, we call it hardware queue. But when we are using commands, for example configuration of the hardware queue or verification of hardware queue, we will use TX ring. Actually, in the conversation we say hardware queue. In for example iOS or in CLI we call it TX ring, but you can say TX queue or transmit ring. All of them are acceptable. All right, what is the function of the hardware queue? It is so easy. Assume that in one router, okay, you know that we have a CPU, for example, and after that, when we have a line with, for example, the capacity of sending traffic, we should receive the traffic from the router 1, and after that from the one interface, and then we should forward the traffic to other interface. For example, here, assume that R1 is sending traffic to the destination of the PC2 or PC1 to PC2. This traffic, after verification, after checking with the routing table, should forward to this interface. From this interface is serial 10, okay? And because of that, because here now the line is busy, we can take the packet and we can forward the packet. The first packet can be sent easily without any problem. Assume that for the next packet, again, we are receiving the traffic on the fast Ethernet 00. This is the fast Ethernet 00 interface. And again, we should forward this traffic from the serial 10. Okay, the next traffic, this is the first packet. And now we are receiving the second packet, for example, packet 2. Okay, this packet now is receiving by the router 1, but router 1 now is busy. For example, CPU is busy for other functions. Okay, because of that, the line is empty and we can send traffic from the serial 10, but because the CPU is busy, the CPU cannot give us the traffic for forwarding it. Okay, because of that, maybe in some times we should wait, for example, 1 second. Actually now here 1 second, the line is empty, and after that in the next second we can send the packet 2. And it is possible that in sometimes, because of the CPU other functions, we cannot receive traffic from the CPU for forwarding the traffic. Okay, it means that we don't use the line with 100% of bandwidth. Actually, for example, this line, okay, has one or has, for example, 100 bit per second or kilobit per second of the bandwidth, and it means that in 1 second you can send 100,000 bits. Okay, but because in sometimes the line is empty, actually, for example, we are using from this link 64 kilobit per second. Okay, it means that without any queue on this line, on this for example serial 10, in some cases we don't have traffic to send. But what is the solution? The solution is so easy. You can use one hardware queue on this interface. For example, here we have a hardware queue. The capacity of this hardware queue is, for example, 5 packet. Okay, because of that, when we are taking traffic from the CPU, actually we are taking 5 packet 1, packet 2, and then packet 3, and then packet 4, and then for example packet 5, and after that we can start sending the traffic. Actually, always at least we have 5 packets in the hardware queue, and we are sending the packet 1 first, and then packet 2, and then packet 3, and then packet 4, and then packet 5. Okay, and if the CPU is busy and cannot give us in the, for example, immediately the other traffic, we have traffic and we can send them. And maybe for example, now for some amount of time the CPU is busy, we have traffic, and after that when the CPU can give us the new traffic, we can for example again queue those traffic. Actually we can say the hardware queue's objective is to drive the link utilization to 100% when packets are waiting to exit an interface. Okay, the hardware queue holds outgoing packets so that the interface does not have to rely on the general purpose CPU or processor in the router in order to start sending the next packet. Okay, also, as you know, in the hardware queue always we have some packets for send. Because of that we can say always we are using our bandwidth or a committed information rate of the link, and because of that we can use 100% of the for example capacity of the link. But here also we have some other detail. For example, in one router you know that we have control plane, and also we have forwarding plane or data plane. You have learned about them in other courses. In control plane, for example, we have a general CPU, and also in the data plane we have application specific IC or ASIC, application specific integrated circuit. Okay, you know that when the traffic is receiving by the router 1, actually the traffic is forwarding by the data plane, by the ASIC. The good news is that the hardware queue, okay, is controlling with the directly with the for example ASIC. Actually the hardware queue can be accessed directly by the application specific integrated circuit or ASICs associated with an interface. So even if the general processor is busy, the interface can begin sending the next packet without waiting for the router CPU. You know that here when control plane completing the tables in the data plane like the FIB, traffic is forwarding with the help of the FIB in the data plane. Because ASIC directly can control the hardware queue, always we can directly forward the traffic from the hardware queue without the need to wait, for example, for general purpose CPU. And because of that, if the router is busy, again we can send the traffic without waiting for the CPU. You know that because the most constrained resource in a router is typically the bandwidth on the attached interface, particularly on one interface, the router hopes to always be able to send the next packet immediately when the interface finishes sending the last packet. The hardware queue provides a key component to reach this goal. Actually, it means that when we are sending the first packet, immediately we can send the next packet without the need. And this is the function of the hardware queue. But let me to emphasize that hardware queue only is using the logic of FIFO. FIFO, or first in, first out. I will explain the different logics of queuing, but the first in, first out means when a packet entering to this queue, that packet should be forwarded before than the next packet. Actually, the first packet that is inputting is the first packet that is outputting from the queue. First in and first out. This is the logic of the hardware queue. Look at here, this is our hardware queue. Always use FIFO logic. If you want, you can see the hardware queue of the interface with some commands, and also you can tune it. Let me to show you the hardware queue that we have, for example, in the router 1 in the serial 10. Here I'm going to use this command. Look at here, show controllers, then the interface name. For example, here we can use show, okay, for showing the hardware queue. I can use show controllers, okay, and then serial 10. Let me to show you. As you can see in the router 1 show controllers, okay, serial 10 can show us that the TX limited or TX ring has, for example, a length. Here we can see the TX limited. Look at here we have many information, and now I'm not going to talk about all of this information. TX limited is important for us, okay? If you want, you can use show controllers. Okay, show controllers, and then you can use one object modifier, include, okay, include for example, show controller serial 10, then you can use include, for example, TX limited. Okay, and after that you will see easily that the TX limited has this value. Let me to explain the TX limited here. It is so easy. With TX limited, actually you can find the length of the hardware queue here. The length of hardware queue, as you can see now, is 2. The 2 is the length of the hardware queue, and the 0 means now no method of software queuing is enabled on this interface. Actually, here now we are using the default mode. I will explain it, don't worry, but this is important for us now. 2 is the length of the, for example, hardware queue. Also, let me to show you the length of hardware queue on the R1 interface on the fast Ethernet 00. If you want, you can use again show controllers now about the fast Ethernet 00. Okay, and then include TX limited. Here, as you can see, we have for example, the hardware queue with the length of 256. You know that the fast Ethernet 00, okay, has 100 megabit per second of bandwidth. Because of that, here we can gather more packets in compared with the serial 10 with only 1.5 megabit per second of bandwidth. Here, let me to write here for the fast Ethernet 00. In our iOS, we have the length of 256 for the hardware queue, but here in the serial 10 we have the length of 2. All right, this is the story of the hardware queue, but you know that hardware queue only support FIFO logic. Actually, this is a hardware. This is for example, a special type of queue that we don't have any control on this queue. For example, we have many mechanisms about the queuing, about the service of queues. You will learn about them: priority queue, custom queuing, weighted fair queue, class-based weighted fair queue. All of the queues or congestion management tools that we will learn about them in this video and also in future videos are working on this software queues. Actually, hardware queue, as I mentioned before, is a feature of the data plane, okay? And we don't have any control on this hardware queue for enabling different methods of the queuing, okay? Actually, the hardware queue only has one goal. The goal is using the bandwidth or the link utilization, okay, with 100%. That's it. We cannot reorder the packets in the whole hardware queue. Actually, when a packet going to the hardware queue, that packet waits, okay, for sending over the serial 10. But before the hardware queue, when we are receiving the traffic on the router 1, we have software queue. And with the different policies that we can implement on the software queue, we can, for example, give priority to some packets. We can guarantee the bandwidth for some for different types of traffic. Because of that, in this class, in the QoS course, we will work on the software queue only, okay? And after selecting the packets, the traffic is going to the hardware queue only for forwarding. For example, assume that, let me to explain this feature here. In the router 1, now we are receiving two types of traffic. The first type of traffic is data traffic, okay? And the second type of traffic is, for example, voice traffic. Actually, here now we have two types of traffic with different requirement of the quality of service. Both of these two types of traffic are going to one destination. Actually, both of them are going to the 192.168.2. Actually, these two traffic, okay, these two type of traffic, all of them should be sent with the serial 10 toward to the destination, okay? Because of that, both of them now are forwarding, okay, are waiting to forward on the serial 10. But you know that we want to give priority to the VoIP packets, and after that to the data packets. Actually, it means that when we have VoIP packet, first we should send the VoIP packet packet, and after that the data packet. It is obvious because the VoIP, as I mentioned before, is a delay sensitive traffic, and we should send it faster, okay, and sooner than the data. How we can implement it? It is so easy. Look at here. In the serial 10, we can configure software queue. This is the software queue. Let me to use SQ. For example, we have two SQ or two software queue, Q1 and also Qt2. Okay, Q1 is using for the VoIP packet, okay, and Q2 is using for the data packet. Actually, when we are receiving traffic on the fast Ethernet 00 of router 1, after the routing of these packets to the serial 10, okay, actually means after verification of the destination IP and the routing table of router, the traffic should be sent on the serial 10. We can classify these two type of traffic into these two type of queue, the Q1 VoIP and Q2 data, and after that we will give to the Q1, to the VoIP queue, the priority. Actually, it means that the traffic of Q1 should be first sent, okay? After that, you know that here now we need one scheduler. A scheduler can take the packets from the VoIP queue and after that can push those packets to the hardware queue. It is so easy. For example, we are receiving VoIP packet. The VoIP packet is going to the Q1 of the serial 1. This is the first queue of the serial 10, and then data is going to the Q2. And here in front of the queue we have one scheduler. This scheduler can take the packets from the VoIP first, and after that it can push the packet to the hardware queue to be sent. Actually, when the packet from the VoIP queue is going to the hardware queue, that packet is going to send, okay? And here we don't have any other control on that packet. Here you can see the process. Don't worry about this part. Let me to explain only this part. Look at here. We have, for example, three software queues: Q1 for data, Q2 for VoIP, Q3 for example, video traffic. A scheduler, okay, has this responsibility, taking the packets from the queues according to our policy, and after that it can push them to the hardware queue, and then from the hardware queue the traffic going to be serialized, and after that it can be sent on the serial 10. Okay, this is the story of the hardware queue and also software queue. Actually, hardware queue is using for the increasing the link utilization. We are using the hardware queue to drive the link utilization to 100%. Okay, but we are using software queue for applying different type of policy. For example, giving priority to VoIP, or in some cases you will learn that we can use the software queue for bandwidth allocation and some other things. Okay, in the quality of service course, in all cases when we are talking about the for example queue, actually we are talking about the software queue, because we don't have any control about applying policy to the hardware queue. Automatically the traffic from the software queues with the scheduler according to our policy are going to the software queue. Okay, because of that here we have control. For example, in the software queue you can configure different methods of the queuing. One of them is PQ, another is CQ, another maybe is the weighted fair queue. You will learn about them, okay? But all of these policies, all of this queuing mechanism, okay, or queuing algorithm are working on the software queues. All right, but here we have one important note that you should know about it. Maybe you think that the packets or traffic that are receiving from the fast Ethernet 00 after the routing on this to the serial 10, they should go first to the software queue and then to the hardware queue. Let me to write it here. Here maybe you think that we are receiving a traffic from the PC1, okay, on the router 1. This traffic first should go to one of the software queues, okay, and after then after the scheduler selecting the traffic, okay, the traffic is going to the hardware queue. In some cases it is correct, but let me to emphasize that here we have one important note. Assume that the hardware queue, okay, is empty. Actually here in the hardware queue we have space. The length of hardware queue in our scenario is 2, okay, but now the hardware queue doesn't have any packet, okay, and also we are receiving a packet from the PC1. This packet now is receiving by the PC1, okay, on the router 1, and after the routing, the router 1 understand that the packet should be forwarded on the serial 10. Because the hardware queue is empty, we don't use the software queue. Actually, the traffic is going directly to the hardware queue. What does it mean? It means that when the hardware queue is empty, you know that the functionality of hardware queue is driving the link utilization to 100%. Now hardware queue is 0. We don't use the software queue. Automatically traffic and directly traffic after receiving is going to the hardware queue. Look at here. Now you can better understand it here. We have received the traffic. The first verification, the first check is hardware queue full. If, for example, no, it means hardware queue has some space, the traffic is going directly to the hardware queue and it can be sent. But if the hardware queue is full and we have queuing decision mechanism, the traffic is going to the software queue and then to the scheduler and then to the hardware queue. What does it mean? It means that in most cases, yes, it is correct. We are using, because hardware queue has some packets and it is full, the packet is going to the software queue and then to the scheduler, and after that scheduler can forward the traffic or send the traffic to the hardware queue to be sent. But if the hardware queue is empty, has empty space, traffic is directly going to the hardware queue. And here we have one important notation. You know that all of our QoS policing are applying to the, for example, a software queue, okay? And assume that we have a hardware queue with a high length. For example, the length of the hardware queue in the serial 10 is 1000 packet. What does it mean? Now we have 1000 space. Because of that, all of the traffic is going to the hardware queue. And because of that, our QoS policies don't work. It is obvious. Assume that the length of the hardware queue is 1000 packet. Because of that, all of the packets that we are sending, we want to send on the serial 10 include VoIP and data and video, are going to the hardware queue, and the software queue doesn't work, and all of our policies don't work. Okay, because of that, when we want to apply the policy, we should ensure that the length of the hardware queue is a low value, is a small value. For example, 2, for example, 3, for example, 4, 5. Okay. In most cases, when you are applying a policy on one interface, for example, PQ, CQ, or some other mechanism, okay, automatically the length of the hardware queue is decreasing. But if it is not decreased, you can control the length of the hardware queue with this command, tx ring limit a value. Don't worry about the, for example, configuration, because in most cases, maybe in all cases, this decreasing of the length of the hardware queue automatically is happening. But in some cases, maybe you need to control it. This is related to your iOS. But in most cases, I can say that this is happening automatically. For example, in the R1 here, let me to show you. This is the R1. Now, as you can see, we have 256 lengths of the packet, and 0 means we don't have any queuing mechanism on this interface. Let me to enable one queuing mechanism on this interface. The detail of this command is not important for us. For example, priority group 1. Okay, this is the PQ command. Now on the R1, I have enabled on the R1 fast ethernet 00, I have enabled the one method of queuing. Look at here. Again, I'm going to use show controllers fast ethernet 00, include tx limited. Here you can see tx limited automatically decreased from the 256 to 64. And here you can see 1. 1 means one method of queuing now is enabled on this interface. Okay, because of that, automatically the length of the queue decreased to the 64. Okay, if you want, you can decrease more than this. For example, on the interface fast ethernet 00, we can use tx ring limit, for example, 10. Okay, in some cases you are applying a policy, but that policy doesn't work. You want to, for example, give more effect to your policy of quality of service. You can decrease the hardware queue. tx ring limit 10. Now again, in the show controllers fast ethernet 00 include tx limited, you can see the lengths of the, for example, tx ring is there, for example, 10. What does it mean? Now the effect of our QoS policies are more than before. Okay, when a queuing scheduler, this is the queuing scheduler, decide which packet to send next, okay, the packet does not move directly out the interface. as you can see here. Instead, the router moves the packet from the interface software queue to another small FIFO queue, as you can see, on each interface. Cisco calls this separate final queue either the transmit ring TX queue or transmit ring TX ring, okay, depending on the model of the router. Regardless of which name is used, you can call this small FIFO queue a hardware queue, TX queue, or TX ring. Because of that, now we know about the usage of hardware queue. And after that, we know about what is happening when we are receiving the traffic for one interface. If the hardware queue is empty, the traffic is going directly to the hardware queue, okay? And if the hardware queue is not empty, the traffic is going to the software queue according to the queuing decisions. You will learn about them, and then a scheduler can take the packets and it should send them to the, for example, hardware queue. And after that, you know that for applying the quality of service policies, we need to reduce the hardware queue lengths. Automatically this is happening, but if you want, you can control it, okay? With the TX ring limit, okay, you can control it. Here, let me to explain these three commands. With the show interface name, you can see the queuing mechanism that now we have. This can show us the software queuing mechanism. For example, let me to show you this command about the fast Ethernet 00. On the fast Ethernet 00, as you saw, I have configured priority group 1. This is the priority queuing. Look at here, queuing strategy is the priority list. On the serial 10, now we are using, for example, 5.4, first in, first out. With the show interface name, we can gather information about the software queue. And after that, with the show controllers, we can see the physical or the hardware queue lengths, okay? And with the TX ring limit on the interface, we can configure the lengths of the hardware queue. This is the last video we are talking about the hardware queue. In all of the videos, okay, in the quality of service courses, we are working only on software queue, but we should know, we should inform about the hardware queue. It is so important. In some cases, we are applying our policy to the software queue. That policy maybe doesn't work correctly. Why? Because the lengths of the hardware queue is so high and the packets are going directly to that hardware queue, and the software queue actually is bypassing it. Because of that, it should so important for us to know about the hardware queue. In some cases, maybe you need to tune the, for example, hardware queue. From this video, after this video, you will learn only about the different queuing mechanism that we have for software queues, like the PQ, like the CQ, and other mechanism.